Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. So in today's lesson, we're going to look at corrosion. More specifically, we're going to look at the corrosion of steel. Now, steel is 98% iron and about 2% carbon that allows it to stiffen up and be much stronger than just pure iron. There's some other stuff in there like manganese, and depending on where the iron is mined, you'll get other trace elements. But essentially when we say steel, we're really talking about iron. Now, corrosion is a massive problem. It costs billions, if not trillions of dollars in damage every single year worldwide. And so understanding corrosion and how to stop it is really vitally important. So where we should start right now is actually looking at really chemically what is corrosion. So corrosion is when you have moist air interacting with iron. Now, moist air would essentially be oxygen and water. And then, of course, iron is Fe solid. We could include nitrogen in the list because almost 80% of air is nitrogen. The thing is, nitrogen is so inert, it's not part of the reaction. Now, it is important to know that dissolved salts in the water naturally from the ground, or even from salts put on roads, act as the electrolyte in order for this reaction to happen. So looking at our species list, we have a couple of things going on here. So we got water and oxygen acting together as an oxidizing agent. Iron is a reducing agent. Now, water on its own is also an oxidizing agent and a reducing agent. And of course, oxygen is an oxidizing agent as well. However, it's the combination of oxygen and water together as the strongest oxidizing agent. Now, you would find this at positive 0.4 at the electric potential on the data book. And then iron is going to be the strongest reducing agent. So I'm going to proceed to write out the reduction and oxidation half reactions using my reduction half reaction table. So moist air, which is the reduction half reaction because it is the SOA, is O2 gas plus 2 water liquid plus 4 electrons is becoming 4 OH minus aqueous. Now the oxidation half, of course, we have to flip. This comes from the strongest reducing agent. And so it would be Fe solid becoming Fe2 plus aqueous plus 2 electrons. Now, in order to balance this properly, we need the electrons to cancel. So I'd multiply the oxidation half by 2 to give me 4 electrons. So 2, 2, 4. Those electrons would cancel with these electrons. And then I can put together my net reaction. So the net redox reaction would be 2 oxygen gases producing 2 water liquids. 2 oxygen gases reacting with 2 water liquids and 2 iron solids, becoming 2 iron ions 2 plus 4 hydroxide ions, aqueous. All right, we should check to make sure that we have balanced this correctly using oxidation numbers. So 1 times 0 is 0, 2 times 0 is 0, 2 times 0 is 0, 2 times 2 plus is 4 plus, and 4 times 1 minus is 4 minus, so 0 is equal to 0. This is actually only one of multiple steps in corrosion. The iron will eventually end up being iron 3 plus, but this is the extent of the net reaction that we need to know at this point in our chemistry career. So this is corrosion. If I was ever asked to explain corrosion in a long answer, I would always start by actually writing out this chemical reaction and then I can add, a few sentences to better describe what's going on, but essentially it's the electrical interaction between moist air and iron, where iron loses electrons and the moist air gains electrons. The next thing we're going to do is we're going to focus on corrosion prevention. And to be honest with you, the easiest way we can talk about stopping corrosion is to actually focus in on this net reaction. So let's look at the reactants first. In order for corrosion to happen, oxygen and water must come into physical contact with iron. So the easiest way to stop corrosion is don't allow the strongest oxidizing agent to touch the strongest reducing agent. And this is how we do most of our corrosion prevention. So what do we do to cars? We paint them. That paint stops the iron touching moist air, and then the car won't corrode. But of course, if you get a deep scratch which goes through the paint and into the body of the car, then moist air can start to react with the iron underneath the paint, and then it will start to bubble and corrode. So again, the simplest thing to do is just don't allow oxygen and water to touch iron. Painting, using oil, rubber, plastic, grease, electroplating the iron with a different type of metal. Anything that covers the iron up will stop it from rusting, and generally those are usually the cheapest route to go. Now, the next thing we could do is we can attach a metal, which is a stronger reducing agent, to the iron, which would then make the iron not the strongest reducing agent. So I'm just going to throw out one example, okay? If hypothetically we had magnesium solid as the strongest reducing agent, so we actually attach some magnesium to the metal, then it would become the strongest reducing agent. The iron would no longer react, the magnesium would, and the iron would be left alone. It essentially would be a spectator metal. And we would call this a sacrificial anode. We are sacrificing the magnesium, allowing it to oxidize with water and oxygen in order to leave the iron alone. This is very, very popular when it comes to boat protection in terms of corrosion protection. Sacrificial anodes are attached to lots of parts on boats. And they have to be cleaned and exchanged out every once in a while. They do oxidize completely, and then they have to be changed out, as well as many other applications. The last thing that we can do to stop corrosion is actually apply a electrical current to the piece of iron, which is exposed to oxygen and water, to the cathode side of a battery. This would continually feed electrons to the surface of the iron. So we know that electrons move from anode to cathode. So if this is attached to the cathode side of a power source, electrons continually get fed to it. And then the oxygen and water just pick up these electrons that are on the surface of the iron, leaving the iron alone. This is called cathodic protection. And it is very common for any kind of buried structures or pipelines, things like that. So it would be used to protect the metal parts on a tank underneath a gas station, or more relevant to us, on the pipeline here in Alberta. So those are the three major types of corrosion prevention. We would cover the steel, we would make a sacrificial anode onto the steel, or we would supply power, and that would give us cathodic protection on the piece of iron. So what I'm going to do now is just go through these slowly, one at a time, and write some of them down. Okay, so the number one most common thing to do to stop corrosion from happening, is covering the steel, and it's usually the most cost-effective way. So paint is probably the most popular, but also electroplating. the iron with something else. Now, this is very cost ineffective when you're dealing with very, very large pieces of steel. So for instance, you wouldn't electroplate giant steel beams that hold up an overpass. It would just cost way too much. You can use grease because it is water repellent. It's not water loving. It is a hydrocarbon, and so it's non-polar, so water won't go into it. Oil, you could cover things with plastic or even rubber. Of course, these would be smaller items, not really big items. Galvanization is probably one of the most popular ways of coating iron on a large scale. Galvanization is when iron is covered with zinc. Now, this can be done a couple of ways. It can be done through electroplating the zinc on, but they also just dip large pieces of iron or steel in giant vats of zinc, and it coats the whole piece of steel. You'll see this everywhere. So guardrails on bridges, lamp posts, the posts that hold up lights, the inside metal structure of a hockey rink. If you're sitting in the bench and if you look in front of yourself, you'll see all these metal beams. That's all galvanized steel. Cell phone towers. It is actually a massively important way of protecting metal against corrosion. The second way we can stop corrosion of steel is to use a sacrificial anode. And that really means exactly what it says. We're sacrificing the anode of this electrical cell by using a metal which is a stronger reducing agent than iron, and it's just simply attached to it. Since the metal is physically in contact with iron, iron would no longer be the strongest reducing agent. So here, let's look at the half reactions that are relevant. This here, iron, would be my strongest reducing agent in corrosion. Now, we know when you lose electrons, undergo oxidation at the anode, this would be the reducing agent. This is our anode. The piece of iron is an anode in this chemical reaction. Okay. Now, what a sacrificial anode is just a stronger reducing agent than iron attached to it. Well, if you go down, you'll notice that zinc is a stronger reducing agent than iron. So if I essentially bolted a piece of zinc onto iron, it would act as a sacrificial anode. Zinc would then react with moist air, and it would oxidize, and it would turn into a zinc oxide or zinc hydroxide, something like that. This is also possible with chromium, aluminum, and magnesium. Now, this is where I would stop. You would not be attaching a piece of sodium metal to something that is going to get wet, because of course it would produce hydrogen gas and explode. So I'm looking for a stronger reducing agent than iron, so I'm going below iron, but I'm really not going past this point because these aren't realistic metals to be using as sacrificial anodes, just due to their very high reactivity and even explosiveness. They're also very, very expensive. So sacrificial anodes should really only include zinc, chromium, aluminum, and magnesium, or any alloys, which is simply a mixture of these metals put together. So aluminum, magnesium alloys are used very commonly in boating to protect different parts of the boats using sacrificial anodes. Essentially, you would just melt down aluminum and magnesium, you'd put them together, you allow it to cool, and then you would have your electrode. Our last type of corrosion prevention is called cathodic protection. Now again, these is generally used for larger structures, pipelines, large water vessels, and it essentially sets up the piece of iron as a electrolytic cell. So for instance, let's say I had a pipeline and it's buried. So this is a pipeline. And because it's buried, I can't, if I cover it with dirt and rocks after I painted it, it could get scratched and it could then start to rust. And then you can have a break below the ground, environmental damage, say you're moving oil, etc. It's really not wanted. So what happens is the pipeline is made, then we hook up the pipeline to the cathode side of the power source. This would then be hooked up to some scrap metal on the anode side. And essentially electrons would be drawn away from the scrap metal, anode to cathode. These electrons would coat the pipeline, and then the moist air or oxygen dissolved in water in the ground would then pick up these electrons, do its reduction half reaction, but leave the pipe alone, stopping it from corroding. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.